This week I read chapter 8 of Bartle and Sherbert, and let me just show the book. So chapter 8 is sequences of functions. Which of course is sort of like a pre to power series expansions and to Fourier series. Some of the proofs include the use of differences for uniqueness. So for example, there's also these sections on e natural log of x being inverse functions, and then the cosine and sine functions. And so because Taylor expansions with the remainder term are used, it fits with the sequences of functions section. Although and this is I think unique to Bartle and Sherbert of all the books that I'm looking at, I like the fact that I don't think I've seen this material elsewhere. Yeah. So when you get to cosine and sine, all sorts of relationships for cosine and sine are proved without the cosine and sine function being there. So it's sort of like this is what the cosine and the sine function do. Likewise for e and natural log of x. And so a lot of the proofs involve a Taylor expansion for the uniqueness proofs, a Taylor expansion on the difference between two functions, and that because they're the same function, the difference should be 0. And so in the proof, you get rid of all the terms except the last one, which is the remainder term. Then you bound it, take a limit, and it's 0. And that's how you prove that the difference is 0. Therefore, the functions are unique. So this is used for the e and natural log proofs for uniqueness of e, and then also for uniqueness of the sine and cosine. And I'll show my notes. Right now, I am at 30.6% ratio between my problem set pages and reading pages, which is a pretty good ratio. It's pretty high because I just came off of doing some Thomson-Bruckner problems, which I'll return to, but I want to finish reading Bartle and Sherbert. So it's going to be, I finish chapter 8, I'll start chapter 10. 10 is a little longer. I hope to finish it by next Friday, and then I'll be done reading for this book. X to the n, how it flips between n equals n is even, n is odd. If you've never done that, you should try plotting this function in Desmos or elsewhere. Yeah, so the interchanges of limits with derivative integral using this square function. Not square, triangular. What am I talking about? Using the derivative to go into the proof. And then again, as I was mentioning before, Taylor expansions, all the terms except the remainder term drop, bounded, take the limit to 0 and show that the difference between two functions that are the same is 0, and that means that that function is unique. This is all, of course, pre-power series and pre-Fourier analysis work, foundation work. And that is chapter 8 of Bartle and Sherbert.